Thank you. So welcome. I'm very happy to report on something we made with Engine Kim. There's a correct typo. Engine Kim, Stefan Kracz, and Magnus Wallström. And that was something we're banging our heads for the last few years. And I was very happy that finally, we get some, I think something that looked to me like a real progress. So I'm happy to report it. So let's go on and see what's inside. Okay, so our hero here will be some variants of minimum cut problem. So here on this picture, we have got a sink and a source, and I'm always speaking today about edge cuts. So for directed graphs, it doesn't really change whether you're doing direct edge cuts or vertex cuts. There's a really easy reduction for everything, whatever is talking to you. So let's focus on edge cuts. And now I want to cut edges to cut all the paths from S to T. So we are just counting edges. This is easy polynomial time solvable. You learned it at undergrads. So for example, in this graph, you can cut these two middle edges and get a minimum cut between S and T. Okay? So this polynomial time solvable. But say let's make this problem a bit harder. So let's add weights or capacities on edges. So the edges now have capacities, or like the cost of cutting them. You can think of weight, cost of cutting them. And now if I added this, so I made these two edges we cut before quite expensive. So now we'll actually figure out that, for example, cutting these four edges is the cheapest way. Yeah, so I cut this edges, and this cost 4, and I cut all the paths from S to T up there on this picture. And this is still polynomial time solvable. It's slightly more complicated for Fulkerson if these numbers are really given binary and complicated, because things can augment for a long time, but still this is doable. Okay? But let's make our life even harder. Namely, let's try to be by objective. So if we didn't have weights and cut two edges, there were just two edges, like for example this two in the middle to cut. If we care only about weights, then also something can be done. But let's now try to do something in between. Namely, let's have above a cardinality bound and try to minimize weight. So for example, here in this picture, minimum cardinality cut was size 2, minimum weight cut was size 4, so it happens for size 3 cuts. And if you look at this picture for a while, you will notice that you need to cut one of these 6 edges, or one of the one of the more expensive edges on this picture. And then, but apart from that, you can also cheat with two cost 1 edges, so the cost is 8 on this picture. And I think this is the optimum, the minimum weight cut of cardinality at most 3. Okay, on this picture. So I hope you got what the problem is about now. And this problem turns out to be a bit hard. Okay, so let's put it formally. I have got a swing source, weights, and I have got both the cardinality bound and the weight bound if I want to be I want to have a decision version of the problem. And here, like the weights are given as binary numbers, and the budget is given as a binary number. So there can be some complicated numbers happening there. Yeah, so we cannot just depend unary on the weights. Okay. So this is the question of this picture. It was like this guy was the cheapest guy of weight of cardinality 3. Yeah. So as I said, this isn't be hard, and this is the moment when some people usually get confused. Usually think, hey, you should be able to somehow gadget out this weight and cardinalities like added lightweight. This doesn't work. This isn't be hard. If you know the problem of bipartite vertex cover, when you have got separate budgets on both sides, this is also NP hard. And this is very similar, and the reactions are very similar. It's like the same flavor of NP hardness behind these two problems up there. Okay, and we looked at this problem already back in 2017, and at that moment we figured out that if the weights are also small, so if you're trying to do FPT algorithms parameterized by both the cardinality and the weights, then this problem actually becomes a problem where you have got edges, and edges have different colors, and for every color you can have a separate budget to cut, but the total budget for all colors is still bounded in parameter. Then this problem actually becomes FPT, and it's not super rocket science. It's still not trivial, but it's not rocket science. You look at how important separators were defined, and you see that the proof you can actually make it work with like many budgets for many colors up there. Following the same methodology, and this appeared in our APEC paper. But we at that moment observed that really, hey, but if I bound the cardinality and have unbounded weights were not the parameter, then actually, the problem looks like it should be FPT, but our techniques doesn't work for that. Okay, so let's look at it. The point is that this problem, I mean, we don't know the status, we didn't know the status for directed graphs. For undirected graphs, it is FPT for complicated reasons, because there's actually a quite rich theory of how the structure of all minimal ST cuts of size at most k look like in undirected graph. So there's something called tree reduction of Marcin and company. Then there's something called randomized contractions and like similar decomposition techniques, and you can quite well understand like this case of all minimal cuts of size at most k in undirected graphs, but in directed graphs they're much more complicated. So that's why it's not that easy. Okay. Okay, so now comes the observation that maybe some of you may have now. Hey, can you just gadget out somehow like this weights and cardinalities together to make it work? And what makes work is that if you ask for a minimum weight cut, that's at the same time a minimum cardinality cut. So if k equals to the, so now on this talk by lambda here, I will denote the minimum cardinality of a cut between S and T. So like the maximum number of edge disjoint paths from S to T. Yeah? So the maximum size of a flow from S to T, like when every edge has capacity 1. Okay, so if you ask if k equals to this lambda, so you cannot have a cut of smaller cardinality. So this is like the, I mean, so you're really asking for a minimum weight cut among the minimum cardinality cuts. Okay, in this picture there will be 2, and that will these 2 edges in the middle, they have good minimum weight. Okay. Then you can gadget out it, namely you put on every edge the capacity a lot plus a tiny fraction depending on the weight of this edge. Yeah. So a lot means, for example, the sum of all weights and a bit more, and the capacity of every edge is this now a lot plus the weight of this edge, and now the minimum capacity cut becomes the minimum weight cut among the cuts of minimum cardinality. So you want to score as few m's as possible in the cut, and then after that you optimize the weights of the cut. So that's the reduction, and it works if k equals lambda. So if k is exactly the size of minimum cardinality of an ST cut, but when k becomes larger, you can start to cheat it. Yeah, I mean, you can start to have trade-offs between, okay, maybe I will cut a bit less. I mean, depending on what m you set. Maybe cut a bit less and then afford larger weights, or cut a bit more and have better weights. So that reduction stops to work, and that's not surprising because the problem becomes anti-hard in general. Yeah, so it shouldn't work. That's tricks. But for this one works, and now. So, but this is like the way how we're trying to solve this problem parameterized by k. Okay? So what we do, namely, okay, so this is our main theorem saying here. So say we want now the cut of cardinality 3, so we want the red guy, and we want to reduce to the case of maximum flow. We want to reduce to the case k equal lambda. Okay? But by not guessing some edges from the solution and deleting them, but by adding edges to the graph, to actually get a bigger flow. So what you want to do, you want to add edges to the graph so that the flow increases. So in some sense, you break all the minimum cardinality cuts, but you don't want to break the solution. Okay? So you want to add some edges to the graph such that the flow increases, but the solution stays the solutions. And that's stated here. Let me put on this picture, these edges. So if I want to, like, this is my unknown solution. The red thing on the picture is my unknown solution of size 3. And this is the optimal solution I'm looking for. And now I want to make it a minimum cardinality cut in this graph. So I want to add edges so that the flow from S to T becomes free, but still these 3 guys remain a minimum cut, remain an ST cut, remain a cut. And yeah, so I want to do this, and yeah, so I don't know the cut. So what I will be doing, I will be randomly adding edges in a sophisticated manner, so that for every unknown solution with good probability, I won't break it. I won't add edge like circumventing the cuts, like going from the S side of the cut to the T side of the cut. Okay, and this is exactly what we do, and this is exactly what I don't want to tell you how we do it, because I have got only half an hour and I need to decide what I show. So let's now parse the theorem statement. We have got an algorithm which is randomized polynomial time. That in this graph you get you get your graph and you get your bound. What's the size of the solution you don't know, and the solution is the minimal cut. We work for slightly more, but that will be in a moment. And you want to add edges to the solution, so you are adding some arcs. This A is the added arcs, such that the flow increases, and with good probability, so here the inverse FPT probability, there's an inverse FPT probability, the set Z, it stays an SD cut, so you didn't break, you didn't connect S side to D side, and at the same time, you increase the flow so that it became a minimum cut. Okay, and that's what this theorem says. And during this talk, I will talk about applications of this theorem. I won't tell you anything about the proof of this theorem. That's the trade-off I am going to. Okay, is the theorem statement clear? Good.
I have a different question.
Mm-hmm.
Why there is no such a thing that if you try to solve this by criteria as cut, you just increase this large number, then at some point minimal cut could be of the size that you want it to be?
That's a good question. I mean, that you want to play with this M and then say that there's a value of M so that you will exactly hit the correct.
It should be like monotone, right? The higher this penalty is, the smaller your cut gets.
I never thought about it. I would probably make sense to look into the NP-Harness construction and see where it breaks down there. Yeah. Maybe you increase this M, it's fractional, and the flow is fractional and doesn't say anything. I mean, I don't know. Okay, let's. Okay. I don't have a good answer off the top of my head. So let me continue with the prepared material. Okay, so for this bi-objective proofing, we have got with this theorem, we have got a randomized FPT algorithm. Namely, I mean, okay, if you have got success probability something, you need to like inverse this one, repeat it to get a standard constant success probability. So we repeat FPT number of times, get this flow augmentation, add these edges to the graph as undeletable edges, and say, okay, can I now, what's the minimum weight solution among the minimum cardinality cuts? What's the minimum weight cut among the minimum cardinality cuts in this augmented graph? You compute it, and you, from all the rounds, you return the cheapest solution you found. And I mean, with constant probability, you actually at some moment found the solution. I mean, the minimum weight solution to your original question. Okay, so I hope now with this theorem, the application for bi-objective SD cut is clear. So let me try to continue and give you another application. Okay, sorry, before I go to other applications, I want to make a few remarks about this theorem. The added arcs, we can actually add them always in both directions. If you look at the proof, I mean, it doesn't matter for neither of the applications we know, but actually, when we add an edge, we really argue that they're on the same side. So with some probability, so you can add this edge and make them undeletable. We didn't really optimize the exponent, except for the fact that we have the previous version working for undirected graphs, which is a bit less interesting because less interesting problems can be solved in undirected graphs because there are other tools. But in undirected graphs, we can get k log k in the exponent. With directed graphs, we have k to the 4. We didn't work super hard on optimizing it, but there's really amortization scheme. There's a very deep reason to believe that, at least with our proof, the depth of the recursion is at least k squared. So I don't think we can get k log k with our current tools there. So there's some polynomial in the exponent, which is not near linear, definitely, with our approach. I was asked a few times if there's a randomized algorithm. We didn't really try hard to de-randomize it. There is no good reason to believe it's hard to de-randomize, because there's no algebraic strange tricks inside. It's really a very huge pile of color coding tricks, which every color coding trick on its own is somewhat de-randomizable, but because there's a lot of balancing out special cases, it's not obvious that it can be de-randomized, but we didn't like really sit down and try to do it. And there's a slightly more general setting that it preserves not only minimal SD cuts, but like cuts where every edge of the cut really separates something from the source. So it's really like reachable from S to not reachable from S. And so it not only cuts T from S, but maybe some other parts of the graph are cut away from S that are not essential for, that are not reachable towards T, but are cut away, and it still like preserves. And this is important for some applications, which I don't want to talk about now. There are sometimes some problems when you don't know everything you wanted to separate from S at the very beginning, and you discover these parts as you go through them. So these are like some comments. So now I want to argue.
Can I ask something?
Yes.
Yeah. I missed what does undeletable mean. There is no notion of deleting here.
What do you mean? What?
The word undeletable, what does it mean here?
You can, it's like in infinite number of copies of this edge. When you add an edge, I mean, you cannot cut it later in the cut. So whenever you add an edge, you can add like k+1 copies of the same edge and it's still the same. Yeah.
Okay.
Really, in the argument, we are saying, okay, these two vertices, I mean, with some probability are the same of the size of side of the cut, and we are just adding edges in both directions between them, a lot of them. Okay, bundled cut. So this is, I want to now argue that something more general than the previous weighted by criteria cut, but now I drop weights, but you can add weights to this problem as well. But for simplicity, let's drop weights. So say that you have got a digraph, but the edges of the digraph, you want a cut, again, a cut from S to T, but the edges of the digraph are bundled in bundles, in disjoint bundles, and you pay 1 to delete the entire bundle. Okay? So, I mean, so that's like the idea, and I want to phrase it as, I want to find a minimal cut that intersects as few bundles as possible. So if you delete, I mean, that's another way of phrasing the same problem, but I want to think of minimal ST cuts that intersect as few bundles as possible. Okay, so that's like bundled cut. And this problem, okay, if all bundles are singletons, we didn't do anything, this is still a minimum cut. And there is an old W1 hardness proof that if you have got two edges, if bundles are just of size 2, so edges are paired, and you pay 1 to delete both edges of a pair, this problem is already W1 hard when you parameterize by the cut size. It's hard and W1 hard parameterized by the cut size. So it doesn't seem to be anything interesting here, but it turns out there is. So in 2013, on ISA paper, Higgins, Egger, and Marx defined this problem of chain set when the path is bounded, when every bundle is a bounded length path. So in this W1 hardness proof, it's really important that the two edges are completely independent. They are like very far apart of the graph. But if your bundle is just a path, a short path, then the W1, the PT status was open for a long while. And surprisingly, I mean, the reason why they defined it, they were just not looking around, hey, what's next cut problem I want to solve, but they were actually solving something completely different, least H coloring problems, so like very like homomorphism type problems. And they were asking the question, I mean, they were having this conjecture that whenever this coloring for fixed H is polynomial, then the vertex deletion problem, like delete edges to be H colorable, is actually FTT. And they showed that the only case they couldn't solve is the case that reduces to a chain set for constant error, for parameter bounded value. Okay? And this was open since 2013 and annoyingly appears on many open problems since then. And it turns out that we can solve it with the flow-augmentation. Let's try. So just to focus, I want to focus on L equal 3. For L equal 1, everyone is like a single edge, so that's trivial. You can also think that when you have got a path, you won't need to cut two edges in a row on a path. I mean, if you cut one edge, so you separated S from something else, then the next edge starts in something not reachable from S. So you don't need to cut the next edge. So the problem starts to be interesting when the edges paths are rank 3, because then sometimes it makes you save on like cutting the first and the third edge of a path. Okay, so let's focus on this case. You will see all the important ideas in the L equal 3 case. There's nothing more for general L or bounded parameter L. Okay, so I have got every bundle is a path of length at most 3, and I want a minimal cut that intersects as few bundles as possible, like most k bundles. Okay, and so now what we do, we just do flow augmentation. So we are asking about the minimal cut. Bundle is of size 3. As I said, the cut can only contain, like, the only moment when you want to contain two edges of a single bundle is if you contain the first and the last one edge of path of length 3. So you're really cutting at most 2k edges. You can say 3k edges, just like a quite brute force argument, but you're really cutting at most 2k edges to your minimal cut. So you can apply the flow augmentation. So you can add some edges to the graph that are not in the bundles, so that your cut is actually a minimum cut. Okay, so you have got a minimum cut that intersects at most. You want to find a minimum cut that intersects at most k bundles. Okay, that's your goal. So if you have a minimum cut, it makes sense to look at maximum flow. So here in this picture, these are like the flow paths of maximum flow. I draw them at vertex disjoint. They are very edge disjoint, so they meet in one vertex meet, but it doesn't break the picture much. So let's think of the flow paths as on this picture. And now, so now if my solution is a minimum cut, it cuts exactly one edge per flow path and nothing else. Okay, that's like the structure of a minimum cut. So say this is the solution I'm looking for, and it somehow like intersects the bundles, and that's bounded in K information, so I can guess how it intersects the bundles. So for example, the first two flow paths are like on a single bundle, like this is the first edge and the third edge of a bundle. The third and the fourth, and the fifth and the sixth are bundled together on a single bundle, and say that the seventh one is like a bundle on its own, part of the bundle. So I can guess this information. This is something like, this is actually a pairing of paths. So this is like something like n factorial information, something like that. K factorial, sorry. And now let's focus on one pair. So let's focus on this P1, P2 pair. We guessed that like in the solution, we have got like one bundle, where first edge is on the first path and the last edge is on the second path. And let's look at two bundles that cross. Okay? So these are two bundles that cross. I mean, there are some colors of them, like pink and red. And notice that the red thing cannot be the one that's cut in the solution. Because if you cut these two edges of the red guy, this guy, then the pink guy bypasses it and makes it not a minimum cut. Because remember that you can cut only one edge per flow path. So in this case, I mean, you're allowed, once you cut this edge and this edge, you're not allowed to cut anything more on P1 and P2, and you're not allowed to cut anything outside the flow paths. So the pink guy bypasses and destroys the fact that this is a cut, an SD cut. Okay? So the red guy is definitely not part of the solution, so we can discard it from the bundles and make these edges undeletable. So what's your conclusion? Once you do all these reductions, on one flow path, all the bundles that can be possible part of your solution, they're like sequential on this path, they're never cross. They're sequential, so this is how the candidates to cut look like on this flow path, and you can do it on every pair of paths, the same analysis. So you're just choosing one of these consecutive guys on the first pair, one of the zigzags on the third and fourth path, one zigzag on the fifth and sixth path, and one of the edges on the seventh path. Okay, so now we have that structure. And now if you look at some edge or connection between flow paths, this connection like that I drew there, this connection that I draw here, this is really saying that you cannot cut here later and at the same time cut here earlier than this place. That if you cut something here and if you cut something here, then there will be a short still path from S to T, so that's forbidden. So this connection here really says that the first two paths are cut before this moment, or the third and fourth path are cut after this moment. Okay? And if you think about it, you have got this pairs of paths which are like slides where you cut it, like a sliders where you cut it, and you have got these constraints. This slider is earlier than this place, or this slider is later than this place, and this is like all the constraints you have. And this is a polynomial time solvable CSP. I mean, if you have got like unbound like ordered domains and like binary constraints, like this is smaller than this place or this is larger than this place, this is polynomial time, it's reducible to 2SAT. You can notice that it has got majority polymorphism. I mean, use your favorite tool to solve polynomial time CSPs and you're done. Okay, so we solved. This is it. And what I really used, okay, so what I want to say here, okay, so we get the theorem that chain set is randomized FPT parameterized by the length of the path and the cut bounded, which answers the question of fitness agreed marks. It also works in the weighted setting. I mean, in the end, if this, you can do the weighted, like if you want to minimize, I mean, among the things that intersect at most K bundles, the bundles have weights and you can minimize the total weight of the intersected bundles. Yeah, so that's doable. What I want to say here is now, what I really used in the proof is that if there are bundles of like bounded in parameter size, this whole augmentation step works in the augmentation step, I didn't use the fact that there are paths. I just used the fact that there is bounded number of edges I cut. Okay? The moment I used that there are paths, not like independent pairs of edges, there was only one place, and that was this level. That they cannot cross on a single level. That was the moment when I used that this is a path. Okay? So essentially this will work for all bounded cut instances where the bundles are of bounded size and parameter, and the edges of the bundle are somehow like linearly ordered, like they're connected in some path-like fashion. And once you have this insight, you notice that by the same reasoning, you can solve weighted skew multicut, which is, okay, I don't want to define the problem, that's for people deeply into directed feedback vertex a problem, because weighted skew multicut, if you unravel it into like k layers of like what you separate from which, it actually becomes a bundled cut with this linear order in the bundle. So exactly the same algorithm, we even write in the paper as a simple algorithm solves weighted directed feedback vertex of a weighted skew multicut. I mean weighted skew multicut, which is essentially this iterative compression step of the weighted directed feedback vertex. Okay, so we have got this guy as being FPT, weighted FPT, parameterized by the cut size. So I have got a few minutes left. So let me make an outreach slide. So what we are working now, so we have got another ongoing work now in our team. This was motivated by this, you can phrase the change site as a CSP over the binary alphabet. So we can think of like source being the truth, sing being the false, and you want to separate all the implications from the truth to false. You want to not have a chain of implications from truth to false. And like a path is like a chain of implications. X1 implies X2 implies X3 implies X4. And in general, you can ask the question for a fixed binary CSP alphabet language. You want to ask, is the problem delete k clauses to make the instance satisfiable, whether this problem is FPT or not, parameterized by k. And L chain stat is the language which is like a chain of implications up to length. I'll try L plus 1, but whatever. And you can also have these two independent edges as this type of constraint, like something implies something and something implies something. This is like a single constraint, and this deletion is double on hard by the same reduction. And actually, we can prove with some tricks. I mean, we didn't write it down. That, for example, this constraint, you have got two edges, but you cannot have both of them on the S side of the cut. Then this actually is FPT now. So we are asking this question in general to have a dichotomy. Okay, for these languages, you have got FPT. For these languages, this is double hard. And we think that with the current set of tools, we can at least have the dichotomy inside something which is called ID2, which is this. Okay, I'm not here super expert, but these are these languages when every constraint can be expressed as an end of two CNF clauses. Okay, so like all the examples here are really ends of two CNF clauses. So that seems that the current tricks are able to do it. We didn't write it down, so take it with a grain of salt. These are like very fresh developments. So yeah, and we are working on like having full dichotomy here. So this is a work in progress, but also feel free to apply the tricks to your favorite cut problem. Of course, there are a few directly ones want to apply it, and maybe something will work out there. So that's it. Thank you.